Good afternoon, everyone. You are in the BitFlow track today. The talk today is Femtocells, a poisonous needle in the operator's haystack. I have for you Ravi and Nico and Kevin.
All right. Hello everyone and welcome to our talk on femtocell security. Unfortunately, it's only the two of us today since Ravi didn't get a visa in time. So yeah, it's only me and this is my colleague Kevin. So today we give a short introduction into mobile telecommunication and especially into 3G and femtocell technology, so each of you understands what this technology is about. And then we'll show various attacks focusing end users and also network-based attacks in the femtocell ecosystem. All right, I'll hand over to Kevin.
So first I'm going to present what 3G is. 3G is the third generation for mobile telecommunication. In Europe, the 3G implementation is called UMTS. In the US, it's CDMA 2000. It's quite similar, and as we can see, it's rather complex. That's a simplified picture of the architecture, and not each element is multiple of times. There's even more interconnection between them, so it's quite hard to get through, and that's why we name it the haystack, because there are lots of elements packed onto each other. That's the simplified version, and that's enough to understand how it works. On the left side, we have the mobile station. That's the normal mobile phone. It connects to the home node B, the antennas you see on the roofs and everywhere. It's called just node B. The node B is controlled by the RNC, the radio network controller. And the RNC also links to the core network. And the core network is where all the calls, all the data traffic, and so on is routed. So that's really the most important part in telecommunication routing. The access network only binds the mobile station to the core network. Femtocells. What are femtocells? Femtocells are small access points. We've seen the big antennas on the roofs. Femtocells are the smaller version of it. So that's small. They connect to the 3G network, to the operator network. It's UMTS capable. So every phone can connect to these small antennas. Normal phone, you don't need any Wi-Fi or so on. It's like UMTS, it's plain phone. It's very small, so the coverage is not like the big antennas, 2 kilometers. It's only like 15 meters, 25 meters, always depends. Quite easy to install. The user gets it. The user buys it from the operator and installs it at home. So it just supplies power, supplies Ethernet, connected to the network, and the femtocell will automatically connect to the home operator. The technical name in 3G for femtocells are home node Bs. We've seen the node Bs, the big antenna. That's home node Bs, the small antennas that we place at home. And this acronym, H&B, we'll use it in the diagrams because it's the technical name of it. Why deploy femtocells and not more node Bs? Well, femtocells have some advantages to the users. First, it gives 3G coverage. So if you're somewhere lost in a small town, you don't have any 3G coverage, you wish to have one, but the operator doesn't install anything because it's not worth the money, then you just buy it from the operator, and then at home you have 3G coverage. Because you're the only one to use this box, you have high voice quality and high data bandwidth. The femtocell you buy, it's not for all users. It's just for you and the other subscriber you add to it. Not everyone can use his phone and connect to our femtocell. It's a closed subscriber group. Femtocells has also had lots of advantages for the operator, and actually that's the main reason why they are deployed all over the world. The first one is the traffic offload, and that's the most important one. Instead of using the antennas on the roofs for your data bandwidth, when you're at home, when you want to browse, you use the home node B. So that offloads the traffic from the big antennas to the small antennas. That's all, and that's the main point. It's cheap. The hardware costs around $100, $200, depends from each operator. And most importantly, it's also cheap to maintain. So the operator only sends it to you. You pay for it, you install it at home, and you're responsible to make it work. If it has a problem, he won't send a team to repair your femtocell. You just say, OK, please click here, but it doesn't do something else. You have to call the hotline where they earn even more money. And finally, IP connectivity. Previously, in telecommunication system, everything was PSTN, switch systems, switch networks, and now everything goes through IP because it's cheap and it works well enough. How does the femtocell integrate in the architecture now? We've seen parallel to the normal use, where the home node B and the radio network controller is, we have a new system called the home node B subsystem. Here we find the home node B, the small box on the left. And then, similar to the RNC, we have the home node B gateway that's connecting the home node B to the core network. We have additional components, the security gateway and the home management server. The security gateway is there because you connect the femtocell over internet to the operator. So there must be some security mechanism, first only to allow the femtocell to connect there, and secondly, so the calls are not intercepted on the way to internet or altered or so on, and that's why they put the security gateway. Behind the security gateway, there's a home management server. The home management server is there to remotely configure the home node B. The home node B is at the user's home, and the operator has no physical access to it. So they create this service to configure remotely the femtocells whenever they need. You don't need to configure anything. You just need to give it power and to give it network. Here we see, again, the cells, the big cells that we see, 30 kilometers max coverage, and then even more femtocells, picocells, nanocells. The femtocell we have, this one,
Yeah, so
it's connected, so we can't lift it too high, but that's one of them. And it has a lot of interest. The operator have a lot of interest, and there's even smaller, the ATO cells that have been presented at the World Mobile Congress. That's even smaller. You just connect it through USB over your laptop, so you can phone if you have your laptop on your knees, and it's only like 2 or 5 meters coverage. Femtocells introduce a new list of threats. Now the equipment is not in the user's physical access, it's also in the home physical access. So what happens if the user plays with the femtocells? The 3GPP, who does all the standardization for UMTS, have found the threats, have located them, and briefly explained the impact they could have. What we're going to show in this talk is the real practical impact of these threats, because they are vague. They could say, okay, what happens if it does this, then maybe this could happen. But we will see what really are the impact on the network. First, we need a femtocell. We got the one from SFR. That's the second biggest operator in France. It doesn't cost a lot. First, you need a mobile phone subscription, a classical mobile phone subscription, and then you pay 100 euros more to get this small device you can install at home. You just request it from the operator. The hardware, very cheap, an ARM CPU, an FPGA. The FPGA is just there to do the modulation and the encoding of the signal. It's even not required in the new devices, as all the modulation is implemented in the ARM core. As any other router, it just has any Linux software, and to use the UMTS services, to provide the UMTS services, because it's some specific protocol, some specific links and complicated, they just added a lot of software to handle it. It's not free software at all. What's important here is that the operator just buy the femtocells from the vendors. In this case, Ubiquisys is the vendor, and SFR is the operator. He buys from Ubiquisys and just configures it. It just configures software. It doesn't add any software. It's just a small file where it says, okay, now you connect to this security gateway, now you connect to this home node B gateway, and that's all. So all the bugs that's related for the hardware are to blame for the vendor. The vendors are to blame, not the operator. The operator is only to blame for the network problems. Now that we have the femtocell, we need a rogue femtocell. We need to compromise the femtocell. How we routed it, we used the recovery procedure. Like we said, because we want to keep it expensive, no maintenance cost, they put some sort of factory reset. When we press on the button on the back of the femtocell, the recovery procedure starts and the firmwares get wiped out. It downloads the new firmware, it installs the new firmware, it downloads the new recovery the new parameter image, and configures the femtocell. We exploited this one because it has some flaws. The firmware list and the parameter list to configure the femtocells is captured, is downloaded over HTTPS. But as you can see with the mouse here, as you can see here, they provide a server certificate, but they don't use it at all. They don't check the server certificate. So we just provide our own operation, administration, and maintenance server that could provide the firmware list. You just have to install some DNS, HTTP, NTP, and so on. It's not complicated. The second flaw is normally all the firmwares are encrypted and signed. So if you don't have the key, you cannot provide any firmware. But again, a big flaw, the list it gets is not signed. The list where all the configuration is. And in this list, there's the public key. It doesn't even check if the public key is signed or not. It's just install the new public key, and then every firmware that we push is just checked against this public key. So it won't fail. The encryption keys are also located in the firmware list. It's not shown here, but the firmware list is long. It tells only where to download it, how to decrypt it, and where the signature is. This is a very simplified diagram of the recovery procedure because we already presented in previous talks. And we are more concentrated into now using the compromised femtocell and attacking and seeing what's possible to do. So now that we have a femtocell, we want to see how it works. Here, Nico's going to continue.
Yeah. So obviously, we needed a basic understanding of the binaries on the box. And so we did some reversing in the beginning and it quickly noticed that all of the binaries on the box make heavy use of a function called debug trace, which comes from a shared library that all of the binaries use. And additionally, there's a configuration file called local trace config, where you can see a snippet from on the right side. It's basically just a list with array indices of certain logging facilities and their corresponding log level. And yeah, so what we did initially to get some understanding of the binaries and this tracing is just preloading this library function and exporting the traces to an external host so we can get some output. However, we didn't really see much by looking at this. And yeah, further poking at the libozal from where this debug trace function is coming from, I'm not sure if that's very readable. It's yeah. As you can see in this IDA screenshot, you have an option called limited trace, which is compared in the first block in the register R3 with the value 0. And if it's 0, it's the right branch is taken, and the right block at the bottom just sets the corresponding log level. However, if it's not 0, then R5, which at this point is the actual log level of the process, is compared with 1. And if it's bigger than 1, then the left branch is taken and the log level is always statically set to 1. So that was why we didn't see much. So this was one of the first things that we did. We just patched this shared library so to disable this limited trace option. As a result, we got something like this, which is very cool to understand how the binaries work and to also have some kind of test equipment to play with the box and understand 3G better. So as we had that, the question was, what would we do with the box now? And yeah, one of the obvious things to do with the base station is creating an IMSI catcher. So IMSI in this case stands for International Mobile Subscriber Identity, which is just an ID used in the network to identify a subscriber. And basically an IMSI catcher is just a device that acts as a legit operator base station and is configured to use the same country code and network code as, for example, T-Mobile or AT&T, so that a victim subscriber sees this as a legit base station, books into the cell, and the cell then just proxies all requests to the real network. And while doing so, it can intercept communication, change parts of the communication, and yeah. But that's GSM. In UMTS or in 3G, that's considered to be not possible, or people always say use 3G to prevent this kind of attack. And that's because UMTS provides mutual authentication between the mobile phone and the operator network. So if the base station is not legit, the phone will just never use it. And However, also there's a problem when building a 3G IMSI catcher. There's not really any UMTS base station that you can just buy on the public market and operate with software like OpenBSC or OpenBTS. So that's where these femtocells really become handy. So let's talk again about this mutual authentication in the context of the femtocell ecosystem. It's important to say that the mutual authentication is not happening between the base station and the device, but it's happening between the back-end network and the device. So in the case of a femtocell, it's useless, which makes a femtocell a nice piece of hardware to build a 3G IMSI catcher. And it's useless because the femtocell is just going to request an authentication token from the backend network, and when it receives that, it will present that to the phone. The phone will verify it and connect to the network. But the token is not generated on the box. So if you have a rogue device, you can still get a valid token from the operator backend. So how do we actually get a phone into using our 3G IMSI catcher? And it turns out that's pretty easy in the case of this SFR box. So obviously, by design, there's some kind of configuration to configure to do 3G configuration on the device. So on the SFR box, there's a proprietary database based on SQLite to do that. However, it turns out that there's an even more comfortable way, which is a hidden web interface provided by Ubiquitous to allow the operator or technicians to do certain troubleshooting tasks or simple configuration tasks. This shouldn't be accessible by default and also isn't, but if you access the URLs to reconfigure stuff, then there's no authentication. It's just on the index page of the web interface. Yeah, so the first important setting for a 3G IMSI catcher that this box provides is the access control mode. And like Kevin already said, the device is usually intended to be only used by yourself and subscribers that you edit and register with the operator. So that's the closed access mode. And then there's this nice open access mode where when you set this one, subscribers of any operator can just happily connect to the box, which is nice because then by setting this, you can just catch any subscriber of any operator into using this box. Yeah, of course, you also have to set the network code and the country code, and you can even set the string that is displayed on the device, on the mobile phone. So yeah, that's pretty much IMSI catcher functionality by design that just needed to be discovered, and it's pretty simple. And it provides us with a full 3G IMSI catcher. So, like I said, IMSI catchers are usually used to intercept traffic. So let's check how traffic is actually passed to the network in the case of this device. So on the left side, you have the HMB, the femtocell, which is connected to a PC, which is used by us to intercept the traffic. And the IPsec tunnel is established to the security gateway. On the box, this is done with a proprietary IPsec client and a kernel module. And when you have IPsec on a Linux box, there are usually plenty of ways to get unencrypted traffic. There's Netlink, where you can just grab the traffic on the box. You can dump the keys using the IP utility, which was not possible on our box. And instead, we decided to hijack the key management control messages when the IPsec client is passing the key material to the kernel. So we just have to use LD preload again on this message and pass the message, and yeah. The voice data itself is encapsulated in an unencrypted RTP stream. It doesn't have to be encrypted because it's going already over an IPsec connection, and it's making use of the AMR codec, which is a standardized codec by 3GPP for voice communication. But unfortunately, it was using the stream format for which no open source tools, or at least we didn't find any, were available to dump this voice data. So in order to extract the voice, like I said, we hooked the function to extract the keys. we pass the key material to the box that we use to intercept the traffic, where a packet sniffer is running. We then use Wireshark to decrypt the ESP packets of IPsec, and we've written a small open core based utility to convert the AMR codec into WAV files. Yeah, so let's see how that looks in practice. For the simplicity of that demo, I'm just, Kevin, is everything working? Okay. For the simplicity of that demo, I'm just going to call his mailbox. I'm not sure if anyone can hear that.
So here on the right, we see the debug trace here already explained. We see a lot of traffic going on because the phone is connecting. So now we phone.
D'accueil, tapez 2. Pour gérer vos options personnelles, tapez 3. Enfin.
All right, that should be enough. And this could be a victim that is catched by the means of this IMSI catcher.
SMS. And we can also intercept SMS. So now I'm just going to write an SMS. Write message. What's the minute? 35. Just fee. Select. Continue. Test or null, oder?
Nice.
Back. Continue. So we have luck because the network, at the beginning we had some troubles with the network because it was not stable at all. Now we're just going to try to send SMS. SMS is sending. Here you can see a lot of traffic again because it's connecting again to the network to send the traffic. The SMS is sent, and now we're going to decrypt the traffic.
So yeah, for that I'm using just this interception Ruby script, which is doing all the steps that I already explained.
Here we've seen the feed that I just sent.
Media VBox.
Yeah. Go on the left with the mouse.
Do that on your own.
And here we're just going to play player stereo wave, and if the sound is coming
Vous n'avez pas de nouveau message. Menu principal. Pour modifier votre annonce d'accueil, tapez 2.
So yeah, that works pretty simple and is pretty much provided by the box as a feature. So for those who wonder how over-the-air encryption works in the case of the Femtocell, because in 3G usually the voice traffic is encrypted over the air, and in order to do that, the Femtocell needs a key to encrypt the traffic, and this key is usually not shared in the network. It's the network sends a random number that is used, not a random number, but a random challenge that is used together with the phone's SIM card in order to compute a session key. And in the case of the Femtocell, the Femtocell receives this key from the network. As you see in this Wireshark screenshot, this is the red marked message, and it's unknown to Wireshark because this is not really standardized in any way. But by reversing the binary, we found out that this is actually kind of a run-up derivative, and this is a security mode command message. And if we look at this stuff, at this message, we see that it contains the various key parts required to do the over-the-air encryption with the phone. So yeah, that's all done by the box. So how does signaling traffic work with the Femtocell? For that, operators developed a protocol called GAN protocol, which stands for Generic Access Network Protocol, also sometimes known as UMA, Universal Mobile Access. And what this actually is it maps the radio layer, or the layer 3 that you see, the mobility management, the SMS, the call control layer, to a TCP IP-based signaling, TCP IP-based connection. And for each of the subscribers using the cell, you have one of these TCP connections. And whenever the phone is doing signaling, the Femtocell generates GAN messages and encapsulate this signaling. So for the phone, The usage of GAN is actually transparent. It doesn't need any special support. It doesn't have any special stack for that. And the Femtocell does all the translation. So this is interesting if we want to play with the traffic generated from a phone. So in order to play with the traffic, we developed a proxy to proxy all of these GAN messages. And in order to use it, we just reconfigured the box to connect to our proxy instead of the home node B gateway. Additionally, the proxy is able to differ between all the message types, which we need because we also have an attacking client which is talking to the proxy over an extended version of this GAN protocol in order to instruct it, in order to perform certain attacks and with the help of the proxy. So yeah, the proxy and this client are communicating and implementing various attacks that we show now. So the first thing we wanted to do was modifying traffic. By using the GAN protocol, we can modify arbitrary traffic, but we decided to do this with SMS because it's easier to implement rather than having to deal with all the RTP stuff, because SMS is only based on signaling in the Femtocell ecosystem. So here you see an SMS message in Wireshark. It's fairly standard. You have a layer 3 message that just contains of a normal SMS payload like you would also have it in a normal network. So in order to modify SMS traffic, the client is just connecting to the proxy and tells him, hey, I'm waiting for an SMS. And whenever an SMS is sent from a mobile phone, the proxy will see the message type and will forward the SMS to the attacking client, which will then just decode it, adjust it according to our needs, and re-injects it into the network via the proxy. So let's see how that looks in practice.
So switching. Here we have a picture of the phone. The camera has some difficulties because it's very bright in here. I just wrote "we're," and we're gonna change that. You're taking part of this one. I'm sending the SMS. Continue. Sending. Send. And it comes on this phone.
Yeah, I think so.
I'll just put it here.
So the client. Oh wait.
What you see on the left side is the GAN proxy telling what's going on and so on.
Yeah, but
Line released.
there's a problem because let's send another one.
Okay, was too early.
Yeah. The webcam.
The webcam, yep.
Oh, actually we need a webcam so you see what we sent originally. I'm not sure if that's is that visible?
Very bright.
Oh fuck.
But we write weird or weirded.
Okay. Oh, I lost connectivity somehow. Oh, okay, maybe we have to skip this part. Something is not working with the phone.
Okay, I'll try to fix that. You can continue.
Okay, sorry. Okay, we just continue, and you have to believe us that it works. So.
Oh yeah, second one.
Whoops.
No, also this one.
Yeah. All right, so hopefully this demo will work because it's also more cool. So yeah, modifying content of subscribers is one thing you can do, but it's more interesting to impersonate a subscriber. So what about free phone calls of anyone who's booked into your cell? Or what about subscribing a victim to a premium rate SMS service to get some money? So whenever our attack client wants to establish a channel and do a service request on behalf of a victim, it needs somehow to know the identity of the victim, which in the case of a mobile network is either the TIMSI or the IMSI number. So in order to get that, the proxy is not only differing between message types, but it's also caching every subscriber-related information exchanged between the phone and the network. So what happens is our client is just connecting again to the proxy. It says, I need a fresh subscriber information. The proxy will just reply with a fresh TIMSI or NIMSI. And the attacking client is then using this to issue a service request to the network. So that's pretty straightforward. The only problem you have to overcome at this point is that whenever you do a service request in a 3G network, the network requires you to authenticate before that. And that's obviously a problem because the attacking client doesn't know the aforementioned secret key on the SIM card to generate a proper response for that. So to solve that, it pages the victim phone. So paging is a standard way in a mobile network to let a subscriber know that there's an incoming service request. That's what happens before you get a phone call or an incoming SMS. And just in the case just as when we send something, you also have to authenticate when you receive the service. So the phone will happily answer this paging request, and afterwards we can just, like in a classical man-in-the-middle attack with some kind of oracle, we can just forward the authentication request to the mobile phone. The mobile phone will then verify and verify the message and compute a response that it will submit back to the proxy, which just forwards it to the network then. So after this is done, basically we can fully impersonate the victim already. So in this case of impersonating via an SMS, the attacking client just continues to push an SMS message into the network. Yeah, I think we have a demo for that as well, and hopefully it works this time. So
now this phone will send an SMS to this phone without me having to press something. Here we send the GAN proxy, there's a paging request, the phone is paged, download request, update request, that's the authentication. And once the authentication is done, the network is quite unstable. Yeah, didn't match.
Try again. Fuck. Yeah, that's a problem with live demos. Actually, we tested this stuff before. Doesn't work.
Yeah, the network is quite unstable, and that's why it doesn't work. It loses connectivity all the time.
How much time do you have to execute the man-in-the-middle attack? Is there a timeout from the network?
Yes, I don't know what the specific time is, but there's definitely a timer set from the network. And when this, but I don't know how much seconds are set in specific,
So
why
it should work. I'll reboot the Femtocell, and we can try the demos at the end if it works. I definitely
want to show that because live demos are cool. Yeah, I hope it works later, so we can show it maybe at a later point. Fuck. Yeah. So in theory, that would have been attacks on subscribers which are booked into our cell. But what about attacking subscribers who aren't booked into our cell? So one of the attacks that got already published in the past was the so-called IMSI detach denial of service attack, which was discovered by Sylvain Minot and was performed over GSM in the past, but also works in UMTS. So the impact of this attack is that all mobile terminated services are not delivered to a victim anymore. So this means it can't receive a phone call or an SMS anymore until the phone reboots and reassociates properly with the network. The network will just assume that the subscriber went offline. So this is the message that a phone sends when you switch it off and you detach from the network normally. And this works because this message is not authenticated. It's not authenticated in UMTS, it's not authenticated in GSM. So, but the only problem with this attack is normally that it only works with victims which are in a certain geographical area served by a visitor location register. The visitor location register is a local cache which is communicating with a central database in a mobile communication network and is keeping track which subscribers are in a certain area. So what happens if you as an attacker are not in an area served by the same VLR is that the VLR will just not know the victim IMSI that you sent to it in a detached message, and it will just ignore this message and will never mark you as offline in the central HLR, so-called HLR database in the mobile network. So as a result, as I said, users cannot receive phone calls anymore. So, however, in the context of femtocells, the proximity constraint that I mentioned, to be in the same geographical area, is not existent anymore. While testing this stuff, it turned out that all femtocells in the network are handled by exactly one VLR, which also makes sense because you don't only manage subscribers, but you manage subscribers that reside at various places around the world in femtocells. So basically you handle femtocells and not the subscribers directly, and it only makes sense to gather all the femtocells that are in the same IP network and handle them with one VLR. So in the case of the femtocell network, you can detach any subscriber which is using a femtocell in the network because of this one VLR. So just by creating a layer 3 message to craft this IMSI detach message, you can basically detach any subscriber currently booked into the femtocell network. Yeah, I hope at least this demo is working.
We're not booked in, so it should work.
Oh, you restarted.
Oh, okay, now we're booked in. Here, just take place. We can try the injection again, if it works. So now we're injecting, paging request is sent. Is it? No, it's broken.
Okay,
Okay.
That's pretty bad.
It seems SFI is doing some changes to block us. We're going to try to start it again, and we can just continue with the slides.
Oh,
That's a shame because the demos are nice and they all worked.
I swear they worked before. If you want to see them, I will happily show them after the talk if the network works better. I have no idea. Yeah. So obviously it would be also nice to not only attack subscribers in the femtocell ecosystem, but what about attacking other femtocells? So we checked the attack surface that is visible to a remote attacker inside the femtocell network. So on the one hand you have network protocols, and on the other hand you have services running on the box that are also accessible from a remote femtocell. And on the network part you don't have many interesting protocols. You have basically most of the traffic is handled in the IPsec tunnel, and besides that you have heavy use of NTP and DNS, and while both are vulnerable to spoofing attacks, DNS is mainly used for the firmware recovery, and then you would need a way to trigger the firmware recovery, and NTP is only used or mainly used as a clock source to provide frequency stability. So this didn't really seem to be feasible to compromise a remote femtocell. Yeah. So instead we looked at the services, where you on the one hand have a web server that is serving the mentioned web interface, and you have the TR69 provisioning process that is required by the operator in order to remotely configure these devices. And both of these services make heavy use of HTTP, and TR69 additionally uses SOAP, which is based on XML, and yeah, these protocols basically are known, or there were several examples of software stacks implementing these protocols and failing at some point. So we looked at these softwares. Yeah, and also attacking the services directly is interesting because it's an embedded system. So like on most embedded Linux devices, all services run as root. So if you compromise one, you compromise the whole device. Yeah, so we went for the web service, which is based on SHTTPD. That is an open source project that was later relabeled into Mongoose and is also the basis for the YASL embedded web service. And it turned out that all of them are vulnerable to stack-based buffer overflow when processing put requests I have no idea why they even need put requests, and also because the whole file system is only mounted read-only. Sorry, not the whole, but the web path is mounted read-only, so there was no need for that. But yeah, they fucked up processing these requests. And since direct communication between the femtocells in the network is also possible, this bug gives us a nice way to root remote boxes. And yeah, I don't want to talk much about the exploit itself, but you can download it at this URL and do whatever you want with it. But I'm going to quickly show it, and if this one doesn't work, I freak out. So we have a netcat running here that's listening on port 4444, and we have this Python script that is running here. We execute it. This is only against our box now, and yeah, voila, we are root. So we can do things like reading out the local subscriber database, or fiddle with the configuration and reconfigure the device according to our needs, and yeah, basically do whatever we want. So yeah, I hand over to Kevin again.
I'll continue. I think it even works, so you can try injecting SMS while I'll present the demo, the rest of it. So, because communication between femtocells is allowed in the network, we can access the other femtocells, and we already found how to access the web interface. The web interface is also available over the network, so we could access the other femtocell websites and get the subscriber numbers. That's the phone number and then IMSI. The IMSI used, for example, to detach it or anything else. There's also something else that the femtocell does. It scans all the neighbor cells. It's required by the operator to verify the location. It's a security requirement defined by the 3GPP saying, okay, all the femtocells should know where they're located, or at least the operator should know. You can use it, you have a GPS. If the femtocell has a GPS device, it's too expensive. Normally it's not implemented. You can use the GeoIP, but that's not precise enough. And what all femtocell does is they scan the neighbor cells, and then they see the country code, the network code, and the location area code. And this can be used to locate approximately the femtocell. Like when you don't have GPS, when you use a smartphone, you can know where you are because you know the cells that are around. Normally the operator uses it to know where the femtocell is, but since we can access the web interface, we can also grab them, and we could be able to locate the femtocells. We could also grab the numbers and know which subscriber is on which femtocell. Yeah, so what could be done is like this at the end, have a map of where all the femtocells are, and when you click on each element, it could display all the subscribers that are booked into it, if they are active, if they are not active, the identity of the femtocell. If you want to fake another femtocell, why not? That's quite a security, privacy problem, because now we know where, we could know how where all the subscribers are located. And yeah, because the website is not read-only, you can also change the settings. We could also say, don't use the GAN controller from the operator, but use our GAN proxy. So now we could use, or we could tell all the that's this one. We could tell all the femtocells use our GAN proxy, and then the demos we tried to do, like intercepting, injecting traffic, SMS modification, we could do it on all other femtocells and all other subscribers that are booked under femtocell, even masquerading as other subscribers. Not only we could abuse the subscribers, but also the femtocells, because we can push our own configuration. We can completely configure the femtocell and say, okay, don't use this security gateway, use our security gateway. Now, use the femtocell for our operator and our network, not for this other one. You could also push some new firmware images to change the binaries, whatever. Yep, so does it work? You rebooted it?
Looks broken.
It's broken. We just looked at the femtocell infrastructure, the femtocell security, but what about the network security? All the services we showed, the home management system, and so on. Actually, it's not different than any other server. It has normal computers with normal services, Apache for HTTP, SSH, and so on. And by just poking around, we found that the FTP account used by the Femtocell to send the performance measurements telling I've been busy the last hour, or I've not been busy the last hour. The credentials are used for all the Femtocells, and the FTP users are system users. SSH is also open, so you could connect to the SSH, to the server using SSH, and be user there to look around for configuration files or whatever. Just hope that they secured right the read and write permission. Finally, last point we did is we know that the Femtocell connects to the security gateway for protection. It uses a SIM card you put on the back of the Femtocell. What now if you just take the SIM card, configure an IPsec client on any machine, connect the SIM card to the computer, and try to connect to the security gateway using the SIM card on your laptop and not on the Femtocell anymore. By trial and error, because IPsec, we know how it works generally, but in details it's quite complicated. We worked on an IPsec client, and now we can connect to the security gateway using the laptop. We don't have any hardware limitation anymore. We don't have a slow CPU. We don't have a slow network card. We don't have software we have to cross-compile for the network. We can do all the attacks, all the network attacks on the laptop. Also, previously, the telecommunication network was separated from the internet because internet is dangerous, there are a lot of bad hackers and so on, and they wanted to keep the telecommunication network secure. But now that we have this gateway, why not just connect the internet to the telecom operator and see what could happen? Yeah. What could happen? That's free for you. We stopped the research for Femtocell because we only did Femtocell security, no network security. But you could use the Femtocell to do HLR queries or to access other access networks, to access the core network. You can play with the operator infrastructure now, but we stopped there. It's just a view of what could be done in this stuff. We're not the only one who tested Femtocell security. There have been previous years, like last month, THC published their results. They also managed to route it and to use it to do call interception. Samsung has also a Femtocell where the source code is available, where somebody plays with the boot controller. And this only shows that the problem we've demonstrated are not specific to one device or to one operator. The implementation is different. We use a GAN proxy, others have other protocols, they don't use GAN. But the big picture is that the attack we demonstrated, interception, injection, modification, accessing the telecom network, that's affecting all the Femtocells. We want to thank some people who helped us to do the Femtocell research. And finally, if you have questions, the GAN proxy, is it working?
No.
Okay, it's not working.
I have no idea. Actually, it seems also like someone is jamming here, but I wouldn't go as far as blaming this. But yeah, somehow it completely doesn't work as usual.
Yeah, we somehow know because it's jamming, because here it's blinking, and that's telling us there's a poor quality of service, and that shouldn't happen because this cells only scan for the neighbors that normally are in Europe. And because in Europe we don't use the same frequency as here in the US, it seems somebody is playing with the radio signal and blocking our demonstration, but it's live demos, they never work. Yeah, if you have questions or if you want to contact us, all the thing we did, the tools we developed and the information we gathered will be published because we finished with this topic, Femtocell security, and if somebody wants to play more testing the security of the network or the Femtocell, he should go there.
We will also publish the complete framework that we use in order to flash our own rogue firmware on the device. So if you get one of these devices, you can freely play with it afterwards.
So now we're trying a last time if the demo works, and
no, it doesn't.
Does somebody have any question? Sure, in the front row. 37, yeah. This, too fast. This one? This one, the remote route. Oh yeah, for the link, yeah, sure. But the slides will be available, so you can grab them. Any other questions somewhere? I don't see all the hands. Yeah, but then that's it. Does it work? No, it doesn't work.
Yeah,
So
thanks, and sorry for the demo fuck up.